We are ME33 and we're happy to share with you the Lotus Elise FA24 swap, and the team consists of Jacob Krantz, Wyatt McGeary, myself, Michael Schumacher, and Jonathan Vilsack. Just a brief overview, our project was sponsored by IBR, which is I Build Race Cars and Tronix 3D, and the car was provided by the company's CEO, Mike Findler. And the Lotus Elise itself is an aluminum chassis 2ZZ GE powered mid-engine sports car, which is an NA inline four-cylinder. We are going to be swapping it out and replacing it with the FA24 found in the WRX. And modifications that are required are the subframe spacer, the engine cradle, the control arm bracket spacer, as well as the rollover bar backstay spacer.
Starting off with an exploded view, on the left-hand side you can see the rear subframe is separated from the chassis itself. In between the subframe and the chassis, a 70mm spacer for both the driver side and passenger side will be made. If you look on the right-hand photo, up at the top, that is the rollover bar backstay. In between the rollover bar backstay and the chassis, a 70mm cylindrical spacer will be made to accommodate for that space that is made up by the chassis spacer. And directly below that is the control arm bracket. That control arm bracket will be spaced away from the C channel, and a 70mm spacer will need to be made to accommodate for that distance.
Given via the sponsor, we utilized a RevoPoint MyAcro 3D scanner. So as you can see on the left, there's a 3D scan of the engine bay, and the right is the engine and transmission inputted into the engine bay. We utilized Mesh Mixer to clean up them scans, and we were then able to import them into Fusion and model directly off of them. Here are the finalized subframe spacers, the driver and passenger side. We utilize Fusion 360 to model them. And the center picture there, you can see the manufactured components utilizing the machine shop here at Barron. They are made of 6061 aluminum. You can also see the engine cradle end plates that are made of 4130 chromoly steel that will be bolted up to the subframe spacers on each side. Here is the finalized control arm bracket spacer made of 6061 aluminum, and the rollover bar backstay spacer that is made of 304 stainless steel.
This is the finalized engine cradle design. It is constructed of 4130 chromoly steel tubing with an outer diameter of 1.75 inches and a wall thickness of 95 thousandths of an inch. The cradle's single plane design eliminates complex multi-planar bends, which drastically simplifies manufacturing of the cradle. It incorporates two 26-degree bends that you can see in between the two engine mount interfaces. On the left is the cradle mounts. These bolt to the chassis spacers at the 3 bolt flanges, which constrain all degrees of freedom. The planar design positions the engine at a pitch of 4 degrees to optimize clearance and minimize axle articulation angles. On the right are the engine mount interfaces where the original FA24 engine mounts will reside.
Here is the finalized CAD drawing of our cradle that with none of the components attached to it. This allowed us to send it out to the fabricator to have the tubing bent. Here is the overall assembly with 2 different views. As you can see, the engine cradle is holding up the FA24 engine that is directly bolted to the subframe spacer.
Moving on to the finite element analysis of our components, we'll start with the frame spacer. Since the spacer mounts between the chassis and the rear subframe, there will be fixed supports on those 2 interfaces. On the side of the spacer, where the 3 engine cradle bolts are located, there is an applied bearing load representing the weight of the engine and transmission. For the 2 subframe bolts on the fixed interfaces, we applied a bearing load to estimate the forces applied when the car hits a bump. Now the yield stress of 6061 aluminum is 276 megapascals, and the spacer only experienced 14.4 megapascals of stress. This makes this design applicable for our application. Next is the control arm spacer simulation. There are fixed supports applied where the spacer mounts to the C channel. There are also bearing loads applied from a result of the frictional force between the spacer and the control arm bracket, in combination with the bolt preload not being great enough during loading. This then results in a bolt bearing contact. The control arm bracket spacer is also made from 6061 aluminum, which has a yield stress of 276 megapascals. The stress that the bracket spacer experiences is only 18.18 megapascals, making it also applicable. The last component simulated in FEA is the engine cradle. There are fixed supports on the ends where the cradle mounts to the subframe spacer. Then there are downwards forces applied to the engine mounts, which represents the engine and transmission weight. Here shows the results of the equivalent stress. The cradle is made out of 4130 chromoly steel, which has a yield stress of 360 megapascals. The engine cradle only experienced 144.9 megapascals, which is also well under its yield stress.
After verifying our components via FEA analysis and hand calculations, we modeled all of our prototypes using FDM 3D printing, and then we're able to mock up all of these parts on the car to confirm their fit.